This is an example of digital information to contrast with the analog signals we've been talking about so far in the course. In Units 10 and 11, we introduced digital ideas to provide a bridge with the more usual modern circuits which combine analog and digital techniques. A pocket calculator is a familiar example of digital electronics. We can introduce numbers and other symbols here on the keyboard, and we can look at the answer on the display. But I don't want you to get the idea that putting in and getting out numbers, or digits, is what makes the electronics digital. What really matters is what goes on inside. If we look inside, there isn't much to see. Just one digital integrated circuit which does all the work. This has a number of terminals, or pins, on which there are signal voltages. These are binary digital signals which simply jump back and forth between high and low voltage levels representing the binary digits 1 and 0. Now, we can't set about explaining a very complicated integrated circuit yet, like this calculator chip, but we can talk about a simpler circuit, a so-called ROM, which can do some of its functions. David will now show you how a ROM can be used to provide a useful digital display.
I'm going to be looking at the type of display device that you met in Unit 10, the so-called 7-segment display. I'm sure you've seen it yourselves in calculators and watches. As you can see, there are 7 bars or segments which can be lit up in various combinations to form the denary digits. Each segment is turned on or off by applying a high or a low voltage to it, and I can do this with these 7 switches here. If I want a particular combination of segments to be illuminated, then I have to provide the corresponding combination of voltage levels with these switches. I'll call a high voltage level 1 and a low level 0. So at the moment, all the switches are set to 0, or a low level voltage, and so all the segments are off. If I now set them all to 1, which is the denary digit 8, all the segments are on. And some other combinations, like 1, 1, 1, 1, 0, 0, 1, produces the denary digit 3. So I'm applying a 7-bit binary word to the display to control which segments are on or off. So in order to show a given denary digit on this display, you have to represent it by a rather long and arbitrary code. In digital circuits, numbers are not usually coded in this way. A more compact and orderly code is for denary digits to be represented by their equivalent natural binary numbers. This is the form of binary coded decimal, or BCD, that you met in Unit 10. Look at the left-hand column of this table. You'll see the denary digits 0, 1, 2, and so on. Beside these are their 4-bit natural binary equivalents, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. The column on the right gives the 7-bit binary code that lights up segments in the display to form the appropriate denary digit. For example, 3 is 0011 in binary, and as you saw, the corresponding display word is 1111001. Now you'll remember that we call this arrangement of binary data a truth table. An electronic circuit in which the combination of voltage levels at the input and the combination of voltage levels at the output are described by a truth table is called a combinational logic circuit. Here is an example of a combinational logic device. It's called a read-only memory, or ROM for short, and it has the property that we can build in any truth table we choose. This is called programming the ROM. I've programmed one here with the truth table that you've just seen. If I press this switch, its outputs will control the 7 segments in the same way that the switches did. A high level will turn a segment on and a low level will turn it off. The input to the ROM is the BCD code that we saw in the truth table, and it is set up on these switches here. The lights tell us whether they are set to 0 or 1. With all the lights off, the input to the ROM is 0000, and so the denary digit 0 is displayed. If I set 0001, then the denary digit 1 appears. 0010, 0011, and so on through the natural binary sequence. Now, although we've set up this truth table and ROM as a purely static problem, a sequence of numbers could well have come from a device which is counting something. In practice, it could be counting objects passing on a conveyor belt, or cars driving into a car park. or I suppose any other event which can be represented by electrical pulses. So I've now got a counter connected up to the inputs of the ROM. It will count input pulses as a sequence of natural binary numbers. Every time I press this button, 1 is added to the binary number here, and so the corresponding denary digit changes with it. The counter is stepping through the addresses in the ROM, 0100, 0101, and so on. And the denary digits are changed 6, 7, 8, 9, and you'll see that we've arranged for the counter to go back to 0 after it's counted 9. Now I can also produce these pulses automatically. This switch controls a pulse generator which is producing short pulses at regular intervals. We usually call this a clock, and so the clock pulses automatically operate the counter, which counts up to 9 in binary and then starts again from 0. Now in this case, the ROM has been programmed to display the denary digits in their correct order, but this is only one of the many ways that the truth table for the ROM could have been chosen. I've got another one here which is programmed differently. It produces an alphabetic sequence instead. Let me just change it. The counter is still going through the same sequence of addresses in the ROM, but these addresses are now filled with different data. And there are obviously a great many more ways that we could have programmed the ROM. Now, connecting up the 7-segment display to a binary counter like this reminds us that even though the display problem can be summarized in the form of a truth table, which describes a static relationship between its inputs and outputs, in a real world we're often concerned with logic inputs and outputs which are changing with time.
I want to develop this idea by looking at the everyday problem of setting up traffic lights to operate in a prearranged sequence. I'll be using this model of a road junction by way of illustration. Now, traffic lights are ideally suited for digital control because the individual bulbs here can be turned on and off by the application of high and low voltage levels corresponding to logic 1 and logic 0, just like the elements of the 7-segment display you've just seen. There are 2 sets of lights, one set for the main road and the other set for the side road here. 6 lights, so for control purposes I need 6 wires, and these have been brought out to a set of terminals here which have been connected up to these switches. I can use the switches to set up combinations of lights. For example, to set up red here and green here, I can enter the code word 1000001, and there you can see the lights with the code word underneath. To set up an amber state here, I need to alter the code as follows. Keep the first 1, 0, 0, 0, 1, 0. And there again, you can see the code underneath the state of the lights. We can start to build up a list of useful combinations in this way, and I've sorted out 8 combinations in the order that they might appear in a traffic light sequence. We can add an extra column to this list, giving a natural binary number to identify each combination or state of the traffic lights. Now, this isn't strictly a truth table as it stands, but it could form the direct basis for a truth table. For example, we could use the natural binary state numbers as address inputs to a combinational circuit or ROM to set up the traffic lights in a particular state. The diagram here shows the combinational circuit as a ROM. There are 3 address lines, 1 for each bit of the address input, and 6 output lines for controlling the lights. Now, to take the lights through a full sequence, it's necessary to step systematically from one binary coded address to the next. You've already seen how this could be done automatically by using a binary counter to provide the sequence of address inputs. And here it is in the system diagram. The counter is counting pulses supplied at regular intervals from the clock input. Now, I've got a system like this running on the traffic lights here. The terminals which supply the voltage levels to the lights are now connected to the 6 output wires from the ROM. you can see that the lights are going through a sequence at a steady rate controlled by the system clock. Now, I can assure you that the sequence is correct. We could check it out by careful observation over a period of several minutes. All the same, it's worth bearing in mind that many digital systems operate much faster than this. In many cases, it may be necessary to check out a sequence which lasts for only a few milliseconds or even a few microseconds. When things are changing quickly in a circuit, we normally use an oscilloscope to check out the voltage levels. But even this isn't always convenient when the output appears on a bundle of wires simultaneously, as it does here. One way around this problem is to monitor the sequence of states using an instrument like this. You've probably noticed it already. It's called a logic analyzer. The logic analyzer enables us to build up a record of the states one by one as they occur. It's fitted with a multi-way probe, which I'm using to sense the logic levels appearing at the terminals here. Now, this particular analyzer is capable of displaying a 16-bit word across the screen. So there's no problem in accommodating the output from the ROM, which you may remember is only 6 bits wide. I'll now start up the analyzer, and we'll see the sequence being built up state by state on the display. As soon as a state is completed, it's entered into the analyzer display. You'll see the sequence beginning to repeat after 8 states have been recorded.
So you've now seen how a ROM can be used for code conversion in a 7-segment display and in a traffic light sequence. So let's now look at how these sequential methods can be used in more complicated displays. This calculator, for instance, doesn't have just 1, but 8 symbols in its output display. And I've set up the number 1, 2, 3, 4, 5, 6, 7, 8. As each of these has a 7-bit input to control the 7 segments, we would need 7 times 8, or 56 bits, to provide the whole output, or a few more if you include decimal points and so on. It would need a ROM with a lot of pins and a lot of connecting leads to provide all possible 8-digit numbers. It often isn't done that way. Instead, one set of 7 ROM outputs is taken to all of the symbols, and one additional lead to each symbol selects the one to be illuminated. And we've simulated this principle on this computer output display here. When we select the first symbol, we provide the segment drives for the symbol 1. Then we select the second symbol and provide the drive for the symbol 2, and so on in sequence up to 8. If this sequence of symbols is repeated sufficiently rapidly, the persistence of vision takes over and the display appears to be stationary. In fact, you may have noticed that these symbols are not the 7-segment ones we looked at previously. They're in fact more complicated 16-segment symbols, which can produce more convincing alphabetic characters as well, like this. And there are 20 of them. So without some method of economizing by sequential methods, there's an even more awkward requirement of 16 times 20, which is 320 outputs on the ROM. Now this sequential display idea can be carried further, as David will now show.
This display is producing quite a different set of characters, in fact Japanese ones. Obviously the 7-segment and even the 16-segment displays aren't suitable for this. The machine translates from Japanese to English, and so it has to produce our alphabet as well, like this. In fact, the whole translation process is basically code conversion using a very large ROM. But it's the display that I'm interested in for the moment. So here I've got a large version of one character from that display. You can see that there are 35 square segments arranged as 7 rows of 5. It's usually called a 7 by 5 dot matrix display. Now in principle, we could drive this display from a ROM which has 35 output wires, each connected to a segment position. But normally the only connections to the unit are to complete rows and columns, so that we only have 12 wires coming from the 7 rows and the 5 columns. A given segment will only light up when a logic 1 is applied at the same time to its appropriate row and column leads. To generate a character, like this letter A, we use the same sequencing technique that you saw on the multiple digit display, but in this case we are illuminating each row of a single character in succession. Let me slow it down to show this more clearly. To set up a given row like this, we have to apply an appropriate binary word to the column leads and a logic 1 to the required row lead. So in order to generate a character, we need a sequence of 7 5-bit words, which we obtain from a ROM and a counter. And the counter is also used to select each of the rows in turn. Let's see how we can organize a ROM to do this. To display a full alphabet, we obviously need a very large ROM. We divide the ROM into blocks of 7 addresses, each block being allocated to one letter or symbol. For illustration, let's consider only 4 characters. This is the section corresponding to the letter A from the truth table of such a ROM. We identify each block by a 2-bit code and the row number by a 3-bit code, and together these make up a 5-bit address. This particular block is identified by the letter code 00, and the row code runs from 000 to 110. Each 5-bit address in the ROM contains a 5-bit data word which controls the segments in one of the rows. Because the row data is arranged like this in the truth table, the character to be displayed in fact appears as a pattern of 1s in the data column. So let's superimpose them to show this. Now to display the character, we use the counter to sequence through this series of 7 addresses, and we can see this happening again when we reduce the scan rate. In fact, all the counter is doing is going through a sequence of the last 3 address bits. The part of the address that is the character code is obviously unchanged. Now to display any other character, for example the letter C, we have to select the appropriate letter code, in this case 10, so that we jump to another part of the truth table. The counter goes through the same row sequence as before, but this time selecting a different set of data to display the new letter. Now that we've established the principle of generating a single character by a sequence of data from a ROM, I hope that you can see that by rearranging the ROM, we can produce a column-by-column scan. This involves a sequence of 5 words, each of 7 bits, or even a point-by-point scan, obviously 35 single bits. In fact, this way of generating characters lends itself well to TV displays, and it's used in such applications as computer terminals or teletext.
So far, we've only looked at the generation of logic sequences which spend the same length of time in each state. But I think you'll agree that a traffic light sequence which spends the same amount of time sitting on amber as it does on green isn't very realistic. What we need now is some way of controlling the duration of each combination of lights. At the moment, we can say that the traffic lights spend 1 unit of time equal to the time between clock pulses on each position. To increase the apparent duration of a particular combination, we can arrange for a new ROM with outputs repeated over and over for several clock pulses in succession. To do this, the number of lines in the ROM truth table must be increased accordingly. The capacity of the counter must also be increased to provide a larger range of address inputs to the ROM. Let's look now at an alternative way of tackling a sequence with unequal durations. The idea of using repeated states to vary the duration of a particular combination is only satisfactory for relatively small-scale problems, such as the simple traffic lights you've just seen. When we come to deal with more complicated sequences, for example, like those found in industrial process control, the ROM truth table can get very cumbersome, and it becomes very difficult to make even small changes to the sequences. I want to explain now how the idea of coding can supply a more compact solution. We begin with the list of required combinations in the correct order. I've got them here. Now, the next step is to decide how many units of time we wish to spend at each combination, and to express this in the form of a binary code. I'm going to arrange for 4 different durations, ranging from 7 units of time, coded as binary 111, this is for a red-green combination, through to 1 unit of time for combinations which involve an amber light. And you'll see that they're all encoded with their binary equivalent. Now this duration code, as we call it, is programmed into the ROM alongside the code word which controls the lights. Now I've got a system diagram here, and you can see that the ROM output now consists of a 9-bit word. 6 bits to control the lights as before, and a 3-bit duration code, which comes to the output of the ROM. Now this is split off and fed back into the binary counter. The purpose here is to instruct the counter to count the appropriate number of clock pulses before moving on to the next address. We can use the logic analyzer once again to display the output from the ROM as the counter switches from one address to the next. Here we are in the first position of the lights. When the lights change, the first state will be entered into the analyzer. You can see that the ROM output is now 9 bits wide instead of 6. The first 3 bits give the duration code, while the next 6 bits control the lights as before. So, we've reduced the ROM truth table to 8 lines, but we've increased the complexity of the counter circuit. In fact, this may not be a severe drawback, especially when integrated circuit counters are used. These are available with many built-in facilities, including that of registering a predetermined or preset number of clock pulses. What we have gained is flexibility, due to the fact that the ROM is not only storing data, but also a set of instructions to control the rest of the system.
You've now seen how a ROM can be used in various ways, for static code conversion in a 7-segment display or a Japanese translating machine, sequencing through the ROM to provide a traffic light sequence and for other sequential displays, using repeated states to provide an irregular sequence, and finally storing a duration code as well as bits describing the required output. This is an example of the important use of memory to store instructions as well as data, an essential idea in the use of microprocessors. We'll come back to this in Units 15 and 16.